Let me ask for everyone's help this morning. Cell phones, could we please turn them completely off? They're giving us some audio feedback through our webcasting system. So if you'll help us out in that, we'd appreciate it. Let's move on to our next presentation. It's called the Duplicator-Spoiler game for an ordinal number of turns. And from Montgomery Blair High School in Silver Spring, Maryland, right here in the area, we have Jim Pinkerton and Rafael Setra. Welcome, gentlemen.
Hello everyone and good morning. My name is James Pinkerton and this is my colleague, Rafael Setra. This summer, we researched the mathematics of duplicator-spoiler games, also known as Ehrenhart-Frosty games. Now, let's start out by actually playing a game. There are two players, the spoiler and the duplicator, and they alternate turns, like in a chess game. On a given turn, the spoiler selects an element from one of two sets, and the duplicator responds with an element from the other set. The spoiler tries to prove that the two sets are different, and the duplicator either tries to prove that they are the same or delays the spoiler's proof for as long as possible. Here, we have the ordering of the rational numbers and the ordering of the integers. Since this is a game play with ordering, the spoiler can be said to have won if lines drawn from pairs of elements cross. In other words, if the mapping with respect to ordering has not been preserved. So the spoiler, in this case, will use the property of density and the rationals to distinguish the two sets. The spoiler begins with the element 1 on the integers, and we see any response from the duplicator. Let's say 1 on the rationals. Then we see 2 on the integers from the spoiler. And again, any number on the rationals, let's say 2. Now comes the key strategy. The spoiler picks a number between 1 and 2, 1.5. And now there is no element between 1 and 2 to which the duplicator can duplicate, and thus any element, such as 4, loses for the duplicator because lines drawn from pairs of elements have crossed. Thus, the spoiler can win this game in 3 turns. Now, let's try to distinguish these same two structures, the rationals and the integers, but this time with logic. Let's make a logical sentence that's true of the rationals but false of the integers. The sentence, between any two variables or quantifiers, there exists another variable, is true of the rationals but false of the integers. Notice that in the game, we had 3 turns, picking 1, 2, and 1.5. And now, in the logic, we have 3 variables, x, y, and z. The number 3 just showed up twice, and this is no coincidence. There's a tight connection between duplicator-spoiler games and logic. Now, as a result of this connection, there are several applications of duplicator-spoiler games. First, there's the immediate application to logic and to the field of expressibility theory, but then there are also applications to descriptive complexity theory in comparing different complexity classes. There are also more practical applications. We can see if the functions of 2 different programs are equivalent. We can even look into problems in database search. We might want to ask the question, is my language of database search powerful enough to distinguish between the good results and the bad results? Let's play another game. This time with 2 different finite orderings, one of 7 elements and one of 8 elements. This game will take logarithmic time because the spoiler employs a bisection approach. First selecting an element in the middle on the finite ordering of 7 elements, and then there's a response by the duplicator, and then we see left of middle and again in the middle until eventually the spoiler has bisected this set some logarithmic number of times. Thus, any game played on 2 finite orderings will take a finite predetermined logarithmic amount of time to win. Now, it sounds like we have a nice and clean definition of duplicator-spoiler games, and we do. But there is a problem, and this is the problem that originally motivated our research. Sometimes we have 2 different sets, but yet no matter how many turns we start out with, the spoiler can never distinguish the 2 different sets. For example, let's suppose that we have the game played on the ordering of the naturals followed by the integers versus the ordering of the naturals. And let's further suppose that the spoiler begins with 1,000 turns. Now, the best spoiler move is to select an element on the integers, as every element in the naturals has an easy duplicate. But now, the duplicator selects an element in the naturals that is so far out there that even with the bisection approach, the spoiler will not have enough time to win the game. The duplicator can pick an element that is 2 to the 1,000 elements out there. And then, with only 999 turns remaining, the spoiler will need 1,000 log of 2 to the 1,000 turns, and will thus always not quite have enough turns. And this approach can be adjusted to begin with any number of turns, not just 1,000. So even though these two structures are different, the spoiler can never win. So, as a solution to this problem, we've decided to change the definition slightly. Instead of playing games for a strictly finite number of turns, we're going to play games for ordinal numbers of turns. Now, the ordinals in some way are levels of infinity, but with special properties with respect to ordering. When we play games for ordinal numbers of turns, we are going to say that after one turn, the spoiler decrements the number of turns to some ordinal that is smaller than the previous ordinal. For example, if we start out with omega turns, the first infinite ordinal, then after one turn, the spoiler can decrement omega to any finite ordinal. So omega turns is equivalent to delaying or procrastinating declaring the number of turns needed for the spoiler to win the game. Omega plus 1 turns would then be equivalent to delaying for 2 turns. And then an entire system behind the ordinals can be developed. Omega times 2 is equivalent to delaying for 1 turn, knowing how many turns to delay for. And again, omega squared, and we have an entire recursive system built on the ordinals. So in the previous game, which could not be won by the spoiler in a finite predetermined number of turns, now with omega turns, the spoiler can win. This is because it only takes 1 turn for the spoiler to force the duplicator to commit to the number that before we had as 2 to the 1,000, and here we have as x. And then the spoiler can decrement omega to be some finite number based on x, and use the bisection approach to win the game in then logarithmic time. The spoiler can decrement the number to now log of x and win. So we then investigated games played on more complex orderings. We took the integers and embedded them within themselves. By that I mean take a copy of the integers and replace every element with a copy of the integers. And that would form z squared. Similarly, we can find z cubed, z to the 4th, etc. Given this, we found that the game of z to the k plus z to the k versus z to the k takes omega times k plus 1 turns. For a very long time, we thought that we could not achieve games that took omega squared terms. But our most recent research has proved otherwise. Using the definition of a limit ordinal, we've defined the integers raised to the power of omega. And using this, we have a recursive process that begins with the integers and then make it a little bit larger, it becomes z squared, larger, it becomes z cubed, and eventually you take that limit and you get to z to the omega. So given this, we found that this ordering of z to the omega plus z to the omega versus z to the omega takes omega squared plus 1 turns. Furthermore, we've generalized this to raising the integers to the power of any ordinal. And that would be z to the ordinal plus z to the ordinal versus z to the ordinal. In fact, takes omega times that ordinal plus 1 turns. And we use this to generalize this to take the form of 2 orderings that can require any ordinal number of turns. Now I'm going to pass the presentation over to Rafael, who will talk about games played on structures other than orderings.
The games previously demonstrated by James were all games which try to preserve ordering. However, we can also play duplicator-spoiler games with operations. For example, we could play them with addition. The rules of an addition game are similar to the previous game. 2 players will alternate in selecting elements from 2 sets. However, now a mapping of the elements in one set with the other sets must preserve addition. Here we have an example of the addition game played on the rationals and the integers. The spoiler strategy for this game is to select 1 or any odd element in the integers. The duplicator can then select any element in the rationals. Now the spoiler will select half of this element, and notice that x over 2 plus x over 2 equals x, but there is no element in the integers that when added to itself will equal 1. So the spoiler can win this game in 2 turns. A more interesting addition game is the game played on the reals versus the rationals. This is an omega plus 1 turn game. To prove this, we must show that the duplicator can win the game for any finite number of turns. However, this requires a more complicated proof, inspired by the proof of van der Waerden's theorem. But to show that the spoiler can win this game in omega plus 1 turns, we must show that after 2 turns, we can decrement the counter of the game to be a finite number. This is because after 2 turns, the spoiler will have selected a rational and irrational element in the reals, but the duplicator will have to select 2 rational elements. The spoiler can then show that for the 2 elements selected by the duplicator is a least common multiple, but the duplicator cannot do the same for the 2 elements selected in the reals. So through this strategy, the spoiler can win this game in omega plus 1 turns. Another addition game is the game played on rationals by rationals versus rationals. The strategy for this game is similar to the previous game. The spoiler will select 2 linearly independent elements in rationals by rationals, but the duplicator can't do the same in the rationals. So the spoiler will then select the least common multiple of the 2 elements selected by the duplicator, but the duplicator cannot do the same in rationals by rationals. So this game is also an omega plus 1 turn game. We can also extend these games to be played on rationals by rationals by rationals a k number of times versus rationals by rationals by rationals and m number of times, where m is greater than k. The spoiler strategy for these games would be to continually select elements of free bases in the larger structure until the duplicator eventually runs out. Through this strategy, these games will last omega plus k turns. By converting our operation games into games played on graphs, we have been able to show through subgraph isomorphism that our operation games are actually bounded by omega times 2 turns. Here we can see a relationship between our ordinal games and higher order logic. Recall that an omega plus 1 turn game is a game which after 2 turns, the counter can be reduced into a finite number.
1 minute.
The first 2 moves of the game will be related to 2 first-order quantifiers, and declaring the remaining number of turns will be related to a second-order quantifier that takes into account the first 2 selected elements. To summarize our results, we have found a variety of games which require an ordinal number of turns, and we have shown a relationship between these games and higher-order logic. We have also found specific strategies and bounds for our addition games, and we have found an upper bound for operation games. We could further look into the meaning of our ordinal games, and although addition is the specific operation we looked at, we could still look into a variety of other operations, develop new winning strategies, and find new results. And finally, we could play these games on a variety of graphs, which could provide us with even more interesting results. We would like to thank the College Board, the Siemens Foundation, and the judges for providing us with this opportunity.